Hello everyone. So today we are going to start the course on optical wireless communication for beyond 5G networks and IoT. So this is the first lecture in this course module. So today under this lecture we will study about the optical wireless communication technologies. What are the different technologies? What are the research challenges here? So let us start. So as all of you know, the global data traffic is a real problem. Everything is becoming smart, whether it is economy or environment or government or cities or people or transport, smart living. So smart cities basically consist of all these things, and it promotes the interaction between the human and the environment to enhance the reliability, resilience, operational efficiency and energy efficiency. So all these things, they generate a lot of data. So a lot of data is generated, and the bottleneck actually comes from the existing network, because if you see the spectrum available for communication is limited and the data is huge, so it's very difficult to transport this amount of data over the existing network. So let us understand what is network throughput. In the past, the number of simultaneous voice and data connections, they are doubling every 2.5 years, which is a growth of 32% per year. As you see in this graph, on an average, a person consumes about 3.2 gigabit per person per month. And if you try to calculate the network throughput, this throughput depends on cell density, on available spectrum, and the spectrum efficiency. Now, cell density is, you can make it smaller and smaller, but there are issues. You'll have to have more number of transmitters and receivers. Spectrum is limited. Spectrum efficiency, we will understand, this is also sort of not improving with time. So, the spectrum efficiency is defined as bits per second per hertz. How much data you are able to transport over 1 hertz of bandwidth. That is how spectrum efficiency is defined, and there is a limitation to this spectrum efficiency. So the network throughput, if you want to increase the network throughput, you have to increase either the cell density or the available spectrum or the spectrum efficiency. So let us understand about the spectral efficiency part. Now, spectral efficiency of a point-to-point transmission is given by Shannon limit, which is given in this formula, C by B log 2 1 plus SNR. The units are bits per second per hertz per user. Now, if you want to increase the spectral efficiency, then you have to increase the signal power. There are two ways of doing it. Either you increase the signal power or you increase the bandwidth. And with bandwidth, there's a linear relationship. And with signal power, it is logarithmic relationship. So if you want to increase the spectral efficiency from 4 bits per second per hertz to 8 bits per second per hertz, you'll have to increase the signal power by 17 times, which is huge. So, and in this example, this graph is plotted between SNR and spectral efficiency. So if you see here, if you increase the SNR by 3 dB, then you get an increase of 1 bit per second per hertz per polarization. So signal power increasing, that is not a solution, and bandwidth is limited. So the spectral efficiency gains are actually, there's not much scope for increasing the spectral efficiency. And also, if you see the different technologies in the past, initially the engineers were able to increase the spectral efficiency of the system, starting from first generation of communication system to second, which is GPRS, NH, and then third generation, which is WCDMA, and then next generation LTE. But as you see, the graph is sort of getting saturated. So there is not enough scope for increasing the spectral spectral efficiency. So let me also explain you the different generations of cellular networks. Uh, First generation was actually analog, which is AMPS, Advanced Mobile Phone Services. Then the second generation was digital 2G, which was called as GSM. And the third generation was wideband code division multiple access, which is known as WCDMA, and also high-speed packet access, HSPA, CDMA 2000. They were some of the standards of 3G systems. And fourth generation system is long-term evaluation and long-term evaluation advanced. Now currently we have fifth generation of systems. So fifth generation of systems, basically the standards are being done under 3GPP. 3GPP stands for Third Generation Partnership Project. So they are responsible for making the standards. And so they have different releases. So currently we have about release 16, and then release 17 is also about to come. And if you see the fifth generation communication system, there are three basic parameters on which fifth generation system is realized. One is you should have enhanced mobile broadband. The speed should be as high as 20 gigabits per second, and it should support ultra reliable low latency communication of the order of 1 millisecond, and it should also support massive machine type communication, about 2 lakh devices per kilometer square. So these are the three things which 5G system is able to support. And then there is also discussion on 6G systems and beyond. So these are some of the performance targets of fifth generation system. Basically, it gives some targets about the capacity, about the latency, about the energy consumption, about the cost, about user data rates and coverage. And 5G targets for the speed is that you should be able to get 1 to 10 gigabits connection to endpoints in the field, and not theoretical maximum. And also, as far as the latency is concerned, of the order of 1 millisecond end-to-end round trip latency, and 1000x bandwidth per unit area as compared to existing 4G systems. And you should be able to handle 10 to 100 times number of connected devices using 5G systems. And availability is 5 nines, 99.999%, and it should give 100% coverage. And as far as reduction in the network energy usage is concerned, there should be a significant reduction in the network energy usage of the order of 90%. And the battery life should be 10-year battery life for low power machine type devices. So these are some of the aspirational goals of 5G. And we will see how optical wireless communication technology will fit in to meet some of these goals. So this is very basic difference between 4G and 5G technology. 4G, the data rate is about 200 to 300 megabits per second, whereas for 5G, it should be in excess of gigabits per second, should go up to 10 gigabits per second. And as far as latency end-to-end delay is concerned, for 4G is 300 milliseconds, whereas 5G guarantees a few milliseconds, or typically 3 milliseconds. And the spectrum which will be used for 5G new radio is sub-gigahertz, which is 3.4 to 3.6 gigahertz, and also millimeter wave, which is in excess of 20 gigahertz. And also by using millimeter waves and small cells and beamforming and massive MIMO, full duplex, we'll be able to increase the energy efficiency of the system. So now let us see why we need optical wireless, or why we need to go to different spectrum. So this slide basically gives you the difference between RF spectrum and visible light spectrum. So CAGR, that is the growth of wireless traffic, has been 60% during the last 10 years. So if this growth continues, then you would need 12,000 times the current bandwidth. assuming there is not significant growth in the spectrum efficiency. So in 20 years from now, the bandwidth demand for future wireless system will be of the order of 12,000 into 500 megahertz, assuming 500 megahertz is needed by the operator. So which results in a demand of total 6 terahertz of bandwidth. And if you see the entire RF spectrum, that is just 0.3 terahertz. This means a total of shortfall of 20 times. Whereas in comparison, 6 terahertz of bandwidth is just 0.8% of the entire infrared and visible light spectrum. So the future mobile data traffic growth will actually stem from spectrum rather than spatial reuse, because we need enormous spectrum which is not available in RF domain. So we need to switch to IR or visible light spectrum or ultraviolet spectrum to meet in order to meet these future requirements. So this is a comparison of radio and optical wireless system. So if you see the bandwidth, it is regulated in radio systems. There are agencies which regulate this allocation of spectrum for RF. And optical wireless system, there is no such regulation because it uses the visible light spectrum which is coming from, for example, illumination or a typical light emitting diode or some optical source. So there is no such regulation in optical wireless system. Security in radio system is low. In optical wireless, it is high because the light is contained within the room and it is mostly line of sight. So there is better security as compared to radio system. RF electromagnetic interference, it is significant in radio systems, whereas optical wireless is immune to RF electromagnetic interference. Radio system can pass through the walls, whereas optical wireless is contained inside the room, cannot pass through the walls. The technology cost for radio system is quite high, and optical wireless system, it is low. And you have very low beam directionality for radio systems because, one can do beam forming, but up to a certain limit, whereas there is a good amount of directionality which can be achieved using optical wireless system. The available bandwidth, as I mentioned earlier, is very low, and the available bandwidth in optical wireless system is quite high. The transmitted power, there is upper limit. It is restricted because of interference, because you might interfere other communication systems. There is a restriction on optical wireless also, but that is from eye safety perspective and interference perspective as well. The noise sources for radio systems are other users and systems which are currently operating. And the noise sources for optical wireless system comes from sunlight or ambient light. The power consumption for radio system is medium to high, whereas for optical wireless system, because it uses devices which consume very less power, is relatively low. The multipath fading is significant in a radio system, whereas there is no such thing in optical wireless system. So in short, what are the different requirements of beyond 5G and IoT systems? We need high traffic volume. The mobile data volume per area will be 1,000 times compared to the 4G. We need massive connectivity. So 5G, because 5G provides massive connectivity, and the requirement is 10 to 100 times more devices as compared to 4G systems. You require very high user data rate link. So the order of the data which is requirement in 5G is about 10 gigabits per second, which is actually 10 to 100 times higher than 4G. Low energy consumption is very important. So you require low energy consumption, that is 10 times lower as compared to 4G networks, and extremely low latency. So there are certain applications which require very low latency. So the requirement for beyond 5G is of the order of few millisecond or even sub-millisecond for some of the applications. So let us now understand what are the existing wired or wireless access schemes. Now we have so far understood the requirements of beyond 5G and IoT, and let us see what are the existing wired or wireless access schemes. So one of the wired scheme is XDSL. DSL stands for Digital Subscriber Line. It's a copper-based technology. It has very limited bandwidth, where you combine the phone and the data onto the copper network. And the quality of the signal actually depends how close you are to the central office. The second wireless access scheme is RF. So spectrum congestion is one of the issue. Security concerns. It has lower bandwidth as compared to optical bandwidth. And at higher frequencies where you want to have more bandwidth, atmospheric conditions, attenuation because of rain or absorption of electromagnetic waves, it can limit the distance up to 1 kilometer. Another option is cable, shared network resulting in quality and security issues, and it actually gives only low data rate during peak times. Other option for access network is fiber to the home, 100 megabits per second or even more one can achieve, but it is very expensive because you have to lay the fibers all the way to the home, and because of right of way requirement, it becomes time consuming and sometimes may not be practical. The other option is satellite. It is very, very expensive and it has very limited bandwidth. So considering the issues with all these existing technologies, let us see how optical wireless communication can meet some of the requirements of 5G or beyond 5G and IoT systems. So just to explain you about the spectrum of optical wireless, if you see on the top, you have the visible range here, and then you have the IR here, infrared here, and then you have the ultraviolet here. And here on this side, you have the microwaves and the radio waves. And on the left side, you have X-rays, gamma rays, and cosmic rays. So this visible light spectrum is further, you can see the details, which goes from 400 nanometers of wavelength to 700 nanometers. And if you see the ultraviolet, there are different categories here, ultraviolet A, ultraviolet B, and ultraviolet C. And similarly for IR, infrared, you have different categories here. So optical wireless communication actually exploits visible light spectrum, the IR spectrum, and for certain applications, ultraviolet. And as you see here, the theoretical bandwidth is huge here. Visible light offers you about 320 terahertz, infrared theoretically can offer 20 terahertz, and ultraviolet 30 petahertz. So the spectrum is not an issue. You have enormous spectrum. The limitation actually comes from other factors. For example, your devices may not be working at that speed. So one has to do a lot of research in getting devices which can respond to this high frequency. But whereas the spectrum is available, and it is definitely much more than what is available for RF. So basically there are three types of optical wireless communication technologies which will be used or likely to be used in beyond 5G systems and IoT systems. The first one is visible light communication, VLC. So in VLC, it's a physical layer connection between a transmitter and receiver. The transmitter could be a source, it could be a LED light in your room, or one can have laser diode. We'll see under certain conditions only laser diode can be used that we will understand in subsequent lectures. But the transmitter basically consists of either a light emitting diode or a laser diode. And then you have optical wireless channel where the light is propagated from the transmitter, which could be on the ceiling, for example, ceiling of the room. And then on the ground or on the table, you have a device where a photodetector is connected, and photodetector basically converts that light energy into electrical energy, and you get back your data. So the basic VLC consists of a transmitter, could be a LED or LED, and receiver consists of a photodetector. Again, photodetector can be of different types that we will discuss in subsequent lectures. The second option is, the second technology for OWC is Li-Fi, light fidelity, which is equivalent or a higher version of Wi-Fi, wireless fidelity. Because when you want to have a communication, you want to have a bidirectional communication, you want to have high-speed communication, you should be able to support handover from one device to another device, or from one access point to another access point, and you should be able to support mobility of the users. So a technology which fulfills all these requirements of high speed, bidirectional mobility and handover is actually called as Li-Fi, and it uses LED or the illumination luminaire which is there in the room for communication, or one can use diffuse laser diode. I mean, these are different options. And then on the downlink, because it has to support both uplink as well as downlink. Downlink is actually visible light which is coming from this source, and then you have a device here which will have a photodiode or some sort of dongle where the light is received and converted into electrical signals and processed. And similarly for uplink, you can have different options. You can have either IR, one is not able to see physically because this is infrared, you can't see with your eye. Or you can have ultraviolet, and in some cases where eye disturbance does not matter that much, then one can use visible light. Otherwise, most of the times visible light is downlink and uplink is IR, or in some cases one can use Wi-Fi as a uplink. So different options are available in Li-Fi that we will again discuss when we go to detailed discussions on Li-Fi. The third technology is OCC, which is called as optical camera communication. It uses LED array or light as the transmitter, and then the camera of the device is used as the receiver. So it basically is a short range, low data rate applications which will be termed under which will be discussed under optical camera communications. The other fourth technology is free space optics. This is not indoor. I mean, all previous technology which I have mentioned is mainly indoor. This is a outdoor technology, free space optics. Suppose you want to connect, 2 points which are 2 kilometers away, for example, and you are not able to lay, cables because of certain issues, then one can use a free space optics for transmitting or covering that distance of 2 kilometers by installing a laser transmitter or optical transmitter, and then there is a line of sight with the optical receiver, and then one can establish a connection or link between the transmitter and receiver. So this is outdoor. So these are the basic 4 technologies which will be used in 5G and IoT systems. So once again, I'll repeat: visible light communication, this is limited to physical layer, point to point, and Li-Fi, which is bidirectional and supports high data rate, supports mobility, supports handover, and then optical camera communication for positioning and low data rate short distance communication, and outdoor communication, free space optics using laser diode and receiver on the other side. So let us now see what are the different applications of optical wireless communications. So let us start from here. So you can have communication between two chips, for example, where the distance is of the order of millimeter. So this is under the category of ultra short range. So if you want to connect very high speed signal from one chip to another chip, I mean, you can use other techniques also, but there may be some interference. So using optical wireless, you can connect two chips with high speed. So this is application actually, and the typical distance is millimeter, which is there, in the PCB, for example, if you want to connect two chips with high speed, or in data centers, for example. The second is short range. This is of the order of few meters. So the examples are broad area network or personal area network, or underwater communication. If you want to connect, there are divers inside the sea and they want to communicate with the ship, so they can communicate using optical wireless communication. In-flight communication, when you are sitting in a flight, the light overhead, you can always have communication using that light. So those kind of applications are under the category of short range, which is few meters. The next is medium range. Some of the examples are mentioned here, which is one of them is vehicle to vehicle communication. You can exploit the headlight of the car and communicate with the vehicle which is ahead of you, or vehicle to infrastructure communication, from the vehicle to, for example, traffic lights, or from the roadside lamp, or from infrastructure which is situated near the road. So vehicle to infrastructure. So this is typically of the order of few hundreds of meters, typically 150 or 200 meters, or one can use for wireless local area networks or indoor infrared. So these are some of the examples of medium range. Now in the long range, one can use free space optics if you want to cover a distance of, for example, 3 or 4 kilometers using 1 gigabit per second link, and you don't want to install any cable, then one can use this free space optics. So this comes under the category of long range, or mobile backhaul. These are some of the applications of long range. The typical distance is of the order of few kilometers. Another application is ultra long range. That is communication in the space. So satellite to satellite communication, or satellite to aircraft communication, or from satellite to ground communication, they all come in this category. And the typical distances are the order of thousands of kilometers. So as you see here, the use of optical wireless technology ranges from millimeter, distance communication to thousands of kilometers of communication. So it has a wide spectrum of applications. This is a pictorial view of the applications here. As you see here, this is medium range, which is car-to-car communication, or car to traffic light communication. This is short range optical wireless communication, wherein all these parameters, body parameters, if there are body sensors, it can be monitored by a smartphone. This is an example of short range optical wireless communication. This is an example of interchip communication, ultra short range. And this is an example of long range, connecting two buildings, which could be 1 or 2 kilometers away, where laying of fibers is an issue. And this is an example of ultra long range, that is satellite to satellite communication, satellite to aircraft communication, and you can have satellite to ground communication. So basically it covers all facets of communication. So for making any optical wireless system, these are the basic building blocks. So first let us understand the use of optical wireless communication is in underwater, it is in space, and it is in terrestrial, which includes both indoor and outdoor. And all these technologies, they require different type of strategies, different types of design. And for each of these technology, each of these communication, or each of this domain, you require devices and components. You require optical front-end systems. They're all different for different domains. For example, underwater things are different, space things are different, terrestrial again, the design is different. The channel model in each case is different. The data transmission modulation techniques which you require is again different for different domains. Medium access control protocols, interference mitigation and mobility support, and networking and protocols. Let me just explain you one by one some of these things. Devices and components. I mean, we have seen that the bandwidth is enormous. There is a huge bandwidth available. But can I use that bandwidth? The answer is no, because the devices and the components are not available which can respond to that high speed. Still, research is going on wherein we have components and devices which can respond to very high speed. So this becomes a limitation, device and components. And the next is optical front-end systems. So optical front-end systems is basically because you're dealing with the optical signals, and it could be in the IR region. So one has to ensure that the eye safety standards are met, because you should not use high power, the kind of wavelength which may damage the eye. So you have to ensure that the eye safety standards which are all available should be met when you are discussing, communication using optical wireless. You have to also ensure that your mobile terminal, for example, your phone, which is in your hand, is changing the orientation every time. So there is a random orientation of the mobile terminal. So you have to ensure that your system is able to handle that orientation. I mean, you should not be blocked. Suppose your mobile terminal is upside down, even then you should be able to communicate. There should not be any, blockage in the communication. Also, we want to use very large area detectors, because I want to capture the light available coming from line of sight, non-line of sight, so that I get good signal onto the detector. But then the moment I make a large area detector, the capacitance of the device increases, which will limit your speed of communication. So there is a trade-off. And then one can use, concentrators. Again, the physical size of the concentrator, those are some of the constraints one has to worry about. So this is, different in different domains. As I mentioned, these designs, require different for terrestrial, different for underwater, different for space. And also one has to use angular diversity transmitters, because optical wireless is primarily a line of sight technology. And if something comes in between, it will be stopped. So one has to ensure that in order to have continuous reception of signals, one has to use, multiple transmitters or multi-receivers, so that the blockages are taken care of and communication is not disturbed. Channel model is another area which we will study during the course of our course. And it is different for indoor and outdoor. Indoor channel model is deterministic, can be modeled easily, whereas the outdoor channel model is time dependent and it's very complex. So we need to model channel models both for indoor and outdoor, where we have to consider the multipath propagation. The light can come from line of sight, or it can come after reflection. So there should be a good understanding of line of sight components, non-line of sight components. And when you get many components, line of sight and non-line of sight, there may be some temporal spread of the reflected signal. So you need to control that temporal spread. Otherwise, your data rate will get reduced. It also depends on what kind of reflectivity of the material you have, reflectivity of the material in the walls, for example, so that basically it will tell you how much power you receive after reflection. And also you need to consider different deployment scenarios. It could be a office setup, or it could be a factory, or it can be a roadside where you are communicating from vehicle to infrastructure. So depending upon the deployment scenarios, you have to model your channel. So this is another challenging area for optical wireless communication community, to understand, to have good understanding, a proper understanding of channel models. Now you want to have good power efficiency and bandwidth efficiency, and for different domains there may be a requirement of different data transmission techniques. So some of these techniques we will study, for example, on-off keying, or pulse amplitude modulation, or pulse position modulation, or pulse interval modulation. And also, if you want to increase the overall length or distance of communication, then we might have to use coherent optical wireless communication system, which will give you some advantage over the conventional system. And if you want to further increase the data rate, then use of OFDM, that is orthogonal frequency division multiplexing, and also to exploit different colors in the light, white light, one can use a new type of communication, a modulation technique which is called as color shift keying, CSK. So all these schemes we will discuss in detail. There are other schemes also which gives you benefit of, low energy efficiency or low spectral efficiency, high spectral efficiency. And when you're considering bidirectional communication or communication inside the room, for example, in the case of Li-Fi, one has to choose a medium access protocol. This could be a TDMA, could be OFDMA, could be CDMA. There are different medium access control protocols, and depending upon the application, the requirement, whether you want low latency or you require high speed, so you use a particular access control, and using these MAC protocols, you should be able to find out throughput. I mean, these parameters are a concern. The throughput, what is the throughput you are getting? What is the queued packet delivery probability, or what is the end-to-end packet delivery probability, and how much time the node is active, and what is your typical delivery time, that is when the packet first is transmitted, by the time it is received, what is that delivery time. So all these metrics have to be measured for different medium access control protocols. The other issue which one has to consider while designing optical wireless communication design is interference, mitigation, and mobility support. The interference can come from, access point, other access point. For example, if you see here in this diagram, there are 4 access points and there are 2 users. So there may be interference, because if you see the light which is falling from one, this is access point 1, and say this is access point 2. So there is some area where the light is, both the lights are falling at the same place. So there is some interference coming from other access points. So one has to consider while designing such interference, and should have techniques for mitigating such interference. And there can be a possibility that the user density increases, as is shown in this diagram, right? So there are again challenges if the user density increases, also when the access point density is increasing. So you see here about 9 access points. So there may be some challenge because of increased access point density and number of users. And also depends what is the coverage of each access point. So AP coverage, that is access point coverage. So that also is going to affect your design. So while designing your system, you have to take care of interference mitigation, and you should be able to handle the mobility of the users. So this is in brief about the different topics I'm likely to cover during this course. And before I close, just to give you some information about what kind of systems have been experimentally built. So this view graph actually tells you different type of systems which have been designed, and actually there has been significant progress in the last 4 or 5 years. And if you see whether using free space or communication in underwater, OWC community has increased very, very high data rate of the order of, for example, 15.73 gigabits per second using integrated white LED. And this is somewhere here for free space, 2.5 gigabits per second. And underwater, 2.34 has been achieved. And lot of different modulation techniques, started from on-off keying to OFDM, they all have been used. So there has been a good progress in this field, and in years to come, I'm sure this technology will further grow and will meet the requirements of 5G and beyond. We'll start the next lecture with the basic optical sources and optical detectors, which are likely to be used in optical wireless communication. Thank you very much.